The topic of this tutorial is harmonic analysis. We'll review the definition of harmonics, discuss their effects and corrective actions. We'll look at harmonic sources, calculations for K-factor, resonance, total harmonic distortion, and telephone interference factors. We'll also review and compare related standards and demonstrate the process of building a model to run a computer simulation. Harmonics are defined as a periodic wave having a frequency that is an integral multiple of the fundamental frequency. So why are harmonics bad? Harmonics superimpose themselves on the fundamental waveform, distorting it and changing its magnitude. Harmonics can affect the operational efficiency of the power system. For rotating machines, the harmonic effects include increased heating, increased noise, mechanical oscillations and stress, and pulsating or reduced torque. For transformers, harmonics can cause increased heating, increased noise, and increased losses. For cables, harmonics cause increased heating and voltage stress, resulting in reduced life and increased losses. Harmonics can also result in overloaded neutrals. Harmonics can cause increased heating and stress in capacitors, nuisance tripping and misoperation of protective devices, and harmonics can cause interference with communications and affect the reliability of power supplies and other electronic equipment. So what corrective measures are available for harmonic problems? You can install passive filters that trap the harmonic current, install active filters that adjust with harmonic content, utilize natural phase shift cancellation, add impedance such as transformers or reactors to isolate the harmonic sources from the system, replace the offending equipment, or alternatively oversize the power system components to withstand the extra heat and stress caused by the harmonic current. Voltage distortion is the relationship between the harmonic voltage and the voltage at fundamental frequency. Current distortion is the relationship between the harmonic current and the fundamental current. Simply put, harmonics are caused by nonlinear loads. A nonlinear load draws current in a non-sinusoidal fashion, even when the voltage is a perfect sine wave. Examples of nonlinear loads include static power converters, PWM drives, switch mode power supplies, inverters, arc furnaces, fluorescent lights, and ferromagnetic devices. The nonlinear loads are divided primarily into two categories: nonlinear VI sources and converters. Nonlinear VI sources have a nonlinear relationship between current and voltage, such as transformers, fluorescent lights, arc furnaces, and high-frequency sources. Power converters such as adjustable speed drives, static VAR compensators, switch mode power supplies, and UPS sources are less sensitive to supply voltage variation than the nonlinear VI devices. Some examples of measured waveforms and harmonic content follow. The first example is a switch mode power supply, which is primarily third and fifth harmonic. Fluorescent lighting ballast is also predominantly third and fifth. A 6-pulse adjustable speed drive contains primarily 5th, 7th, 11th, 13th, 17th, and 19th harmonics. Another important concept in harmonics is resonance. Resonance occurs when the capacitive reactance equals the inductive reactance. Parallel resonance is most common and occurs when the inductive reactance is in parallel with power factor correction capacitors or other shunt capacitance. Parallel resonant circuits are high impedance paths that increase the harmonic voltage and amplify the harmonic currents. A sample parallel resonant circuit showing the capacitance in parallel with the nonlinear load and system inductance is shown. Series resonance may also exist, where capacitance is in series with the system inductance. Series resonance appears as a low impedance path to the harmonic current. A sample series resonant circuit showing the capacitance in series with the system inductance is shown. A filter is a generic term used to describe equipment used to reduce harmonic current or voltage. A tune filter generally consists of capacitors, inductors, and resistors in a combination that creates a minimum impedance for one or more frequencies. The minimum impedance creates a path of least resistance for the harmonic current to flow and to be trapped out of the network. Transformer losses and heat are increased with nonlinear loads. K-factor is a specification of how much extra heat a transformer is designed to withstand. The eddy current losses and heat are proportional to the square of the AC frequency. The RMS current is the square root of the sum of the squares of the harmonic current at each harmonic order times the harmonic order. For example, given per unit current values of 0.978 for the fundamental, 0.171 for the fifth, 0.108 for the seventh, and 0.044 for the 11th, the K factor is the fundamental current squared times 1 squared, the fifth harmonic current squared times 5 squared, etc. Adding up the values results in 2.493. In other words, there will be 2.493 times as much heat produced by the nonlinear current than there would be from the same RMS value of linear current. We must therefore select a transformer with a K factor of at least 2.5. Another way to demonstrate that the higher frequencies cause more heating is to plot the K factor versus harmonic content for each harmonic order. 20% 13th harmonic current results in a K factor of about 8, whereas 20% 5th harmonic results in a K factor of less than 4. The heat is proportional to the square of the frequency. Harmonic current can also interfere with communication systems. The interference is a function of the amplitude and the frequency of the harmonic current. A relative measure of possible telephone interference can be quantified by calculating a telephone interference factor. The telephone interference factor calculation uses the RMS current or voltage at each frequency with a weighting factor for each frequency relative to the total RMS current or voltage. The telephone interference weighting factors are published in the IEEE 519 standard and were derived from empirical tests. Another measure of possible telephone interference is the inductive influence, which is calculated from the current at each harmonic order and the associated telephone influence factor for the harmonic order. To better understand a computer model for harmonic analysis, performing a simplified manual calculation is helpful. For this example, we are given a 6,000 amp harmonic source with a 30% fifth and 10% seventh harmonics, a single 1000 kVA transformer with 1000 volts on the primary and 100 volts on the secondary, and a 300 MVA fault current source from the utility. Using an arbitrary 100 MVA base, we calculate a per unit impedance for the utility. Since the per unit impedance is equal to the 100 MVA base divided by the 300 MVA contribution and the square root of R squared plus X squared, using an X over R of 15, R equals 0.022 and X equals 0.33. Similarly, the per unit impedance of the transformer is 0.5 R and 5X. Since the transformer size is 1 MVA, the base is 100 MVA, and the impedance was given in percent. To obtain the equivalent network impedance at bus 2, we can simply add the impedance of the utility and the transformer together. The big difference for harmonic analysis is that you need to calculate an equivalent impedance for each harmonic order. For the fifth harmonic order, the resistance doesn't change, but the reactance is increased as a multiple of the harmonic order. The result is the equivalent per unit impedance at the fundamental frequency is 5.35, the impedance at the fifth harmonic frequency is 26.67, and the impedance at the seventh harmonic frequency is 37.33. Knowing the network impedance at each frequency and the harmonic current at each frequency, the harmonic voltages can be calculated. Our base current at bus 2 on the system base is 100 MVA divided by 100 volts times the square root of 3, or 577,350. The fifth order harmonic current is 30% of the 6,000 amp fundamental current divided by the base current. The seventh order harmonic current is 10% of the 6,000 amp fundamental current divided by the base current. The fifth order harmonic voltage is the per unit current at the fifth times the equivalent impedance at the fifth, and the seventh order harmonic voltage is the per unit current at the seventh times the equivalent impedance at the seventh. Using 96 volts as the fundamental voltage from the load flow, we can calculate the RMS voltage and voltage distortion. Similarly, the fifth harmonic current to bus 2 is 30% of the 6,000 amp fundamental current, or 1800 amps. The seventh harmonic current to bus 2 is 10% of the fundamental current, or 600 amps. The total RMS current is the square root of the sum of the squares, or 6,293 amps, compared to the 6,000 amps of fundamental current without the harmonics. The total harmonic current distortion is 31.6%. This is of course a simplified calculation at a single bus in a two-bus system, and with one source that has only two harmonic orders. The addition of a parallel path, such as a capacitor, complicates the calculations, as does adding multiple harmonic sources and increasing the size of the system, but the overall procedure is the same. As in the case without the capacitor, we first calculate the per unit impedance of the utility, the transformer impedance, the per unit impedance of the capacitor, and determine the equivalent impedance at the desired location by adding the impedance from each of the components. Note that the shunt capacitor requires the addition of parallel components. This calculation is for the fundamental 60 Hz frequency. The same procedure is required for each frequency where harmonic source current exists. This calculation is for the fifth harmonic, or 300 Hz. This calculation is for the seventh harmonic order, or 420 Hz. Using the fundamental current and a base conversion, we can calculate the harmonic current and voltage for each harmonic order, as we did in the previous example. Knowing the current and voltage at each harmonic order, we can once again calculate the RMS voltage, current, and the total harmonic distortion. While it's important to understand the calculations, it's typically not practical to use hand calculations. Our simple example included only one harmonic source with two harmonic orders, no motors, and one capacitor. We were therefore able to ignore triplet harmonics and phase angles, and we only calculated one point in the system. When multiple harmonic sources exist, it's important to include the phase angles in the calculations. The reason we perform harmonic calculations is that we can use the model to predict harmonics, evaluate design solutions, and properly size equipment before the system is built, thereby reducing downtime and equipment damage. Computer simulations are required to effectively perform harmonic calculations. As with our manual calculations, the computer model represents the system impedance as a function of frequency to determine the effects of nonlinear loads on the system currents and voltages. The nonlinear loads are represented as constant current harmonic sources. To build a computer model for harmonic analysis, you need to enter the system network connections, available short circuit current from the utility, rated size and subtransient reactance of rotating machines, rated size and type of static loads, and cable and transformer line impedances. You also need transformer impedance, voltages, and connections, capacitor and filter sizes, and harmonic source size and spectrum. You may also need to evaluate alternative loading and operating conditions for the system. Cables are typically represented as a linear impedance, where the reactance increases linearly with frequency. For long lines, you may need to represent the cable capacitance to evaluate resonance. Nonlinear modeling with distributed capacitance is typically not necessary for industrial commercial applications. While there is some nonlinearity in the transformer impedance, it is typically represented as a linear impedance where reactance increases linearly with frequency. The transformer phase shift is important to include in the calculations, and saturation may result in harmonic contributions. Harmonic source information can come from a variety of places, including from published manufacturer data, field measurements, predicted values, or from typical data. Sample measurement values for a 6-pulse adjustable speed drive are displayed. The harmonic study options include a frequency resonance scan used to identify resonating frequencies in the system, voltage and current distortion, harmonic load flow showing total RMS current and voltage, filter design and evaluation, and telephone interference calculations. The first step in building a system model is to develop a one-line diagram. You then specify the system component details, run a load flow to evaluate the system at fundamental frequency, run the frequency scan, run the current and voltage distortion calculations, evaluate the results, then make any necessary design changes and repeat the calculations. Now we'll build a simple computer model and run the harmonic analysis module HighWave in the SKM Power Tools software. We'll start by creating a new project. We'll call it Harmonics. This creates a blank one-line diagram where we'll add 3 new buses. Next, we'll add a utility source, a transformer between bus 1 and bus 2, and a cable between bus 2 and bus 3. That will feed a motor and a non-motor load. The next step is to enter detailed information about the components. We can start with bus 1 and enter the voltage at 4,160 volts. For bus 2, we'll enter 480 volts. We can select a cable from the library. We'll choose a low voltage copper, magnetic PVC, and we'll make it a size 2 aught, 100 feet long. For the transformer, we can also select from a library. I'll select a dry type, 1000 kVA. For the utility, we need to enter the available short circuit current. We'll enter 300 MVA for 3-phase and 100 MVA for line to ground. We'll leave the default X over R of 8. For the load, we need to enter the rated size. I'll enter 100 kVA. And for the motor, we'll enter the rated size as 100 horsepower. We have now entered sufficient information to run a load flow and a short circuit study. Go to Run, Balanced System Studies. We can check Demand Load, Load Flow, Short Circuit, and click Run. There are no errors or warnings, so we can close the study message dialog. We can next apply data blocks on the one line to look at the steady state results. I'll select load flow power data. This shows we have a 2% voltage drop at bus 3 under normal steady state conditions. It also provides us the power and the current flowing through the cable in the transformer. To perform a harmonic analysis, additional information is required about the nonlinear loads. If we assume, for example, that this motor is an adjustable speed drive, and this load represents fluorescent lights, we can double-click on the motor, select the harmonic source, and go to a library to pick a typical harmonic source. In this case, I'm going to pick a typical 6-pulse IGBT drive. Similarly, for the load, we can go to the harmonic source, select the library, and choose fluorescent lights. A quick way to look at the detailed harmonic source data is to click our right mouse button and select the Go To library. That will open up the fluorescent light library, and we can view the specific magnitude and angle of the harmonic entries. For the fluorescent lights, predominantly 3rd harmonic and 5th harmonic. Similarly, we can select the motor, click our right mouse button, use the Go to Library option to see the entry for the typical 6-pulse IGBT drive. This is the waveform. This is predominantly 5th, 7th, 11th, 13th, 17th, and 19th harmonics. We have now entered sufficient information to perform a harmonic analysis. The first step is to identify which buses we want to report voltage distortion and which branches we want to report current distortion. We can either draw a box around the buses and branches that we're interested in, or we can hold down our Shift key and select or deselect items individually. Once we've selected the components, we can click our right mouse button and use the Go To High Wave option. That brings up a blank study and a case where we'll add these buses and branches we've selected. So in case 1, we have bus 1, bus 2, bus 3 that will show voltage distortion, and the cable and transformer where we'll show current distortion. The harmonic analysis module is broken into 3 windows. There are 2 windows to display graphics and 1 window to show the case. We can resize each of these windows individually. To perform the harmonic analysis, we can simply select the Run button. This provides a study dialog where we can enter a report name for the input data, load flow, and harmonic analysis information. We click on the Run button. This runs a distortion analysis and a frequency scan. To plot the results, we simply select the bus we're interested in or the branch we're interested in displaying. This shows us the current distortion through the cable and the transformer, both in a waveform and in a distortion spectrum. Any combination of components can be displayed in the graph window. If we turn off the cable and the transformer by double-clicking on them, we can turn on the voltage distortion for the bus at bus 3, the voltage distortion at bus 2. To change the plot display, we can select the display area and choose the graph button, and that will display, in this case, scan magnitude. Click it again, it goes to the scan angle. Click it a third time, it goes to the waveform, which we have shown above. Fourth time goes to the distortion spectrum, showing the percentage of 5th, 7th, 11th, 13th, and so on. The scan magnitude is reporting the impedance at the bus location looking out into the system. Note that the equivalent impedance increases linearly with harmonic order. So as the frequency increases, the impedance increases. That's because we have no capacitance in the system. If we were to add a capacitor, it could dramatically affect the impedance of the system. As an example, let's return to our one-line diagram. We'll extend bus 2 and add a capacitor. Double-click on the capacitor and use the filter designer. We can enter the kVAR of the capacitor. Let's enter 100 kVAR. That'll calculate the microfarads of the capacitor. We can now go back to our harmonic analysis and rerun the study. Since I want to compare with the capacitor to without the capacitor, I'm going to copy this case and paste it back in the study folder. And I can rename this case, call it 100 kVAR. And now I can run this case by selecting it, clicking on the Run button. To compare the results, I can double-click on bus 2 and bus 3. Look at the difference that we see in the impedance. At the 13th harmonic order, we have a large spike in the impedance, causing resonance in the system. The resonance and high impedance path increases the voltage distortion at the bus and produces a substantially distorted waveform that has high amounts of 13th harmonics. The graphical display can be customized, printed, and saved in a variety of file formats to include in your reports. To customize the display, select the Plot Properties menu, where you can change the axis range in units, plot styles, graph fonts, colors, grid specification, and add custom annotation. In addition to the graphical display, HiWave has a variety of reporting options. Under Document Report, we can select the standard HiWave report. This report provides a detailed view of the total voltage distortion at each bus, the total current distortion through each branch, and a detailed spectrum for each harmonic order at each bus and through each branch. It also provides the information for the filter design, where it compares the limits with the actual currents. Another reporting option is to use Crystal Reports, which is a third-party reporting package. We select Document, Crystal Reports. We can choose a HiWave default report, which provides us with information about the buses, the branches, filters, and all the other components in the system. Another reporting option is to return to the one-line diagram and apply a data block format that displays harmonic information. We have a default called harmonics. This provides the voltage distortion at each bus and the current distortion through each branch. It also can list the RMS current, which you can compare to the fundamental load flow current. Another useful reporting option is a data block report, which is similar to applying a data block on the one line, except it puts it in a spreadsheet. We say run data block report and puts the same information we're looking at, but in a spreadsheet that can be saved as an Excel file or a report format. When running a harmonic analysis, it's important to understand the various study options that are available. If we go to Run, there's a Setup button that allows us to choose from a variety of study options. These study options include setting the maximum harmonic order included in the calculations and the definition of the PCC, or point of common coupling. There is still some debate regarding the definition of the PCC in some applications, so you may need to discuss the options with your local jurisdiction. For the frequency scan setup, you can choose a self-impedance scan where the current is injected at each bus separately, or you can choose a mutual impedance scan where current is injected at each harmonic source location simultaneously. The self-impedance scan is most common. You can also choose the positive, negative, and zero sequence impedance networks in the scan. Most people prefer to use only the positive sequence impedance since it's easier to identify resonance conditions. Normally it's sufficient to calculate the impedance only at each harmonic order. However, for a more complete scan that includes the peak impedance point, many engineers prefer to calculate the impedance at multiple steps between each whole harmonic order. Highwave allows the impedance to be calculated up to 10 steps between harmonic orders. For the distortion setup, you can choose to use the load flow results as the initial conditions for the distortion calculations, or you can assume a 1 per unit voltage. For distortion calculations, engineers usually include all three sequence networks, such that odd harmonics flow through the positive sequence impedance, even harmonics flow through the negative sequence impedance, and triplet harmonics flow through the zero sequence impedance. The zero sequence impedance may be substantially different from the positive and negative sequence values. You also have the option to represent load impedance as a series RL circuit or a parallel RL circuit. At higher harmonic orders, many experts believe that the load impedance is better represented as a parallel RL circuit. Another important topic for harmonic calculations is to understand the related industry standards. In the United States of America, we follow the IEEE 519 standard. In many parts of Europe and Asia, the IEC 555 standard is used. The IEC 555 standard sets harmonic content limits for individual pieces of equipment. Each class of equipment must comply with fixed limits of harmonic current. The IEEE 519 standard evaluates harmonic levels at the point of common coupling with the supply service entrance. It does not specify limits for individual pieces of equipment. IEEE 519 limits are provided for the total harmonic distortion as well as for the distortion at any single harmonic frequency. For example, the total voltage distortion limit at the point of common coupling is 5% for all systems below 69,000 volts. The IEEE 519 standard also limits the current distortion as a function of load current and available short circuit current. We'll look at a sample calculation to better understand how the load current and short circuit current affect the current distortion limits. We first calculate the available short circuit current at the point of common coupling. The point of common coupling is generally defined as the service entrance from the utility connection. For our example, we'll use the point labeled PCC1. We next calculate the total RMS current. For this example, the fundamental load current is 1000 amps, and the harmonic currents are 90 amps of fifth and 44 amps of seventh. This results in a total RMS current of 1005 amps. The total demand distortion is calculated by dividing the square root of the sum of the squares of the harmonic currents by the fundamental current. In this case, the total demand distortion is 10%. The ratio of the short circuit current to the load current at PCC1 is 283. Since 283 is between 100 and 1000, the total demand distortion limit is 15. Since our total demand distortion is only 10% and the limit is 15%, our case passes the 519 total current distortion limit. It is also necessary to check the distortion at each individual harmonic order to verify compliance. The IEEE 519 and IEC 555 standards are completely different in approach and application. The IEEE 519 standard is concerned with system-wide harmonics and how they affect the utilities. The IEC 555 attempts to limit harmonics at each individual device. The primary advantage of the IEEE 519 is that it includes the effects of natural cancellation, where individual harmonics at different phase angles can effectively cancel each other. The IEC 555 looks to reduce harmonics at the source, which is good in concept but difficult in practice. The IEEE 519 only looks at the point of common coupling with the supply source and is not directly concerned about the harmonics within the local power system. Since the IEC 555 does not look at the overall system, replacing one drive with a lower harmonic producing drive could result in increased overall harmonics if some natural cancellation was lost. To meet the IEEE 519 standard, you need to know the available fault current, the total load current, and the harmonic currents and voltages, either from measurements or from a computer model. The primary advantage of building a computer simulation model for harmonic calculations is that you can evaluate proposed system designs before the system is built, reducing downtime, equipment damage, and ultimate cost. For additional information about harmonic analysis software, contact SKM Systems Analysis Inc. at www.skm.com or email to sales@skm.com.